In this video, I will explain what the Gaussian elimination method with pivoting is and why pivoting could be necessary. So if we take a brief look at how the Gaussian elimination method works, well, we have our dense linear system here on the left, which we convert then to an upper triangular system using forward elimination, and we finally find the solution through back substitution. Now, a clear observation is that these pivot elements, A11, A22 prime, A33 prime here, they play a crucial role in the overall algorithm. And this happens actually both during forward elimination and during back substitution. They have an important role. However, certain problematic cases can occur based on your matrix A. Let's investigate what would happen if we have a zero pivot element. So if our matrix has, for instance, a 0 here in the first row and first column, then by trying to do row reduction here by doing row operations, well, we would compute the ratio between this coefficient and this pivot element, which is 0. So we divide by 0, which is obviously not defined. Now what we can do is a simple solution. We can simply exchange rows here. So we exchange the first and the second row, and that's what we call pivoting. And in this case, well, we will avoid having to divide by 0 when we do the forward elimination. So let's take a look at how this would work for this example. So we have a matrix here which has a 0 in this first row, first column position. And if you solve this by hand or by computer, well, the actual solution to this is as follows. However, if we try to use the algorithm provided in the previous video on this system, the output will be not a numbers only. Why? Because that algorithm does not take into account that this is actually a 0 and it does not do any pivoting automatically. However, if we exchange those rows before feeding this matrix to the algorithm, well, then we see that the outcome actually is correct. So this is something that you would ideally have your algorithm check by itself and do this pivoting automatically. Another bad case, let's say, that you can occur is if you have a singular matrix. Now, if you have a singular matrix, for instance, when a full row of the matrix is equal to 0, so the rank of this matrix is less than 3, it has a 0 row. Well, in this case, this system has no solutions. So for this first row, the equation reads that 0 is equal to 1, which is obviously an inconsistent equation. It's also possible that there are infinitely many solutions. So we have a full 0 row, which is equal to 0. There will be only 2 basic variables and 1 free variable here. So this system has infinitely many solutions. Now for both cases, the Gauss solver that we discussed earlier would result in not a number solution, because again, it would somehow divide this all by 0. Whereas a smart solver should definitely warn you that the matrix is singular. Now, another pitfall is the possibility when we have a very small pivot element, which is not equal to 0, but quite close to it, or at least smaller than the other elements within that row of the matrix. Let's take a look at an example. For the following system, so we have here this linear system, which we will solve using 4 digits precision. And by a quick inspection, you can actually see that or verify that the analytical solution to this system would be equal x1 is equal to 10 and x2 is equal to 1. We solve this system using 4-digit precision. So we first cast this into a matrix system. And immediately we already see that we have here a first rounding error where this 12.343, which has 5 digits, is then rounded to a 4-digit precision representation of that number. Now we want to do forward elimination of this matrix, so to convert it into a upper triangular form. And the first thing that we would do is, well, we calculate this ratio between the element that we want to set to 0 and the pivot element. And if we compute this ratio, we see that this is 1440.33, which in 4-digit precision gets rounded to 1440. So this means that we want to subtract from the second row the first row times 1440, and that is what is shown over here. And let's compute each of these elements. So this is 1440 times 12.34, that would be 17,769.6, which gets rounded to 17,770. And here then we subtract 1 from 17,770. And on the other side, we subtract 5. So 5 minus 17,000, etc., which is rounded to minus 17,760. And this 1 minus 17,000 is minus 17,769, which with 4 digits precision gets rounded to this here. So we see that 1 minus this 17,000 is actually equal to that number. So this 1 gets completely rounded out. So if we fill in the matrix using these 4 digits accuracy computations, well, now we have it in an upper triangular form, so we can do back substitution. So we start with the second element, the second unknown x2. So the right-hand side divided by the diagonal coefficient, and this is 0.9994. And this is quite okay. This is pretty close to the real solution of x2 is equal to 1. However, let's take a look at our first equation. So in the first equation, well, we perform the back substitution, so we get 12.34 minus 12.34 times x2 divided by the pivot element. And this turns out to be 33.33. We see that clearly something must have gone wrong. This is very far from what we actually have in this analytical solution. And this is because we have severely polluted our numerical solution with these rounding errors. And so there is a rounding error on x2, but that rounding error gets then further amplified by dividing it with this small pivot element. So that's very problematic. However, we can try to avoid this situation by switching the rows. So we do pivoting in this case. So we switch this row with this one, and then we end up with this matrix over here. So now this pivot element is, well, much larger than this one, and it's certainly not, well, it's of the same order of magnitude as this element of 1. So let's do then a forward elimination on this. Well, again, we compute the ratio of these two numbers, so the one we want to eliminate with the pivot element, and round it to 4 digits. Well, this is 0.006943. We compute then what this element will be, what this element in B will be, and there is rounding error. So we do see that, well, the multiplication of this coefficient with 5.321 is so small that subtracting this actually leads to having completely the same coefficient in both the B vector, but also here in the matrix. So there is certainly rounding error playing a role here, and these are the impacted numbers over there. But now that we have it in triangular form, let's see whether these rounding errors actually result in a big loss of accuracy. So we can do our back substitution. So this last row, x2 is 12.34 divided by 12.34 is 1, which coincides with the true solution. And then for our first row, well, we work out the back substitution. And in this case, well, it actually turns out that we get exactly the analytical solution in our numerical solution. So here the rounding errors cancel out. Now, this is a fabricated case, and we got kind of lucky here. But let's take a look at what would happen if there actually were rounding errors on our first component that we computed of the solution during the back substitution, so on x2. If there were a rounding error on x2, for instance, of the same level of the rounding error that we had in our initial unpivoted system, well, then if we perform the back substitution, we see that this rounding error does not get amplified as much as it did in the original system. So still here, although rounding errors are present in the solution, they are not strongly amplified. Now this pivoting, well, it basically means that sometimes we want to exchange rows for certain reasons, either to remove zero pivots, which cause the Gaussian elimination method to crash, or to avoid these small pivot values that amplify rounding errors, as we saw in the previous slide. However, this is a minor modification to this Gaussian elimination algorithm, as we will see actually. So here we have such a Gaussian pivoting function, and this is one of the example functions provided to you with the textbook. And actually we see, well, it consists of two parts, the forward elimination part, the back substitution part, and only a small percent of the actual code. So here it does some checking whether this pivot coefficient is equal to 0, and then it will do a row exchange. This is quite simple code. There are some conditions that are checked, and if they are fulfilled, then you just switch row J with row K in here. But all the rest of the machinery of this Gaussian elimination method remains intact. So this is a minor modification that you can do to your algorithm, which can really avoid these detrimental cases where your method would either crash or when you would really introduce big rounding errors because you have small pivot elements. Now, in order to avoid the latter case, well, we would need an additional test here, which tests whether the pivot element is small, or which kind of sorts the pivot elements based on their absolute magnitude, and then always selects the largest pivot element to be used in the forward elimination. But that's not done in this algorithm over here. It just checks whether the pivot is 0.